All right, so welcome back to another video on this lecture series about statistical mechanics and thermodynamics. At its core, statistical mechanics gives us a method to calculate things like the entropy and the free energies that we have yet to talk about so far in this series. But at its core, that's really all statistical mechanics really is. With entropy being perhaps the most important quantity from a foundational perspective. Entropy is a function in our context of energy, volume, and the number of particles in our system. Now, just to give you a sneak peek, we will introduce this concept much more rigorously later and actually provide a more foundational argument for it. But we can actually write down quite easily the expression for entropy, and then you'll see how it's sort of related to counting problems. And its expression intimately relates it to microscopic physics. It's more or less a counting problem related to the microscopic physics. So let's just write it down real quick. So entropy S is equal to the Boltzmann constant, KB, times ln of W. So this is the natural log, and W is the number of, I'll just abbreviate here, of accessible microstates. So when I say accessible microstates, I mean, for this equation, what that means is energetically accessible microstates. Or in particular, it's the number of microstates that correspond to our macrostate given to us by E, V, and N. So this equation probably seems very mysterious as it's given here. You know, it's just a natural logarithm of some counting problem. But we're actually going to provide some nice motivation for it in a few videos. So definitely stick around and you'll get a much more intuitive picture of why we use this quantity in particular. So in past videos, what we did is we defined temperature in the following way. We have 1 over the temperature is equal to the derivative with respect to entropy, the partial derivative, with respect to the energy here. So the derivative of S with respect to E here, entropy with respect to energy, where we're going to keep volume and the number of particles fixed. And this is the definition that we will take of temperature, but in the preceding videos, particularly the videos following this video, we will talk about why we use this specific definition and why it's useful. So in particular, what we'll show in a future video is that two bodies that are in thermal equilibrium will have identical temperatures. But this is for next video. Right now, we have some other things to briefly talk about. So we have this quantity S, which I will write again for convenience. And in particular, S is a function of E, V, and N. And for most systems that we're going to be interested in, as we increase energy, W, or the number of energetically accessible microstates, will also increase. What we might expect, or what we find usually, is that S is monotonically increasing with energy. Okay, so if I increase the energy, I increase the entropy. And what's really happening there is when I increase the energy, my particles have way more ways to organize themselves to fit inside of our macrostate. So more energy means access to more configurations, basically. So with the idea of entropy being a monotonic function with respect to energy, what that means is that we can likewise rewrite our function or invert this relationship and say that energy is also a function of entropy. And if I was to be rigorous here, I would write ESVN. So this is also a valid macrostate. So then from this expression, And our previous sort of discussion on equations important and math important for thermodynamics, in a previous video, we can easily arrive at the equation that we discussed for the second law of thermodynamics. So for now, let's just hold n fixed to make our lives a little bit easy, and we will write the total differential for the energy. So that is dE is equal to the change in energy with respect to the entropy. And what we're going to do is we're going to hold volume fixed here, of course. And then we have the total differential of entropy plus the change in energy with respect to changing the volume. And for this partial derivative, we will hold entropy fixed. And then here we will have dV. So this here is something we have already defined. So this is just the temperature T. And this is the change in energy as we change the volume of a system. So what we'll do is we'll identify this as a pressure. From here, you get your equation from, very simple considerations and definitions. So another way to think about this portion of the expression in particular is that if we were to do mechanical work to a system, so the amount of mechanical work done would be the pressure times the change in the volume. So in this video, what we're going to do is we're going to introduce somewhat of an variational statement of the second law of thermodynamics. So consider a system that I will inevitably poorly draw here. And we will split it into two. Specifically, we might have a system that has a total length here that we might call L, and then we will set an internal constraint here called lambda, where this wall separating the two subsystems is a length lambda L from the left-hand corner, or something like this. So we'll let this partition be free to move. So intuitively then, the equilibrium configuration is going to be one where the pressures coming from either side will cancel each other out. This is an example of a physical constraint we could put on a system. So it's definitely not the only example. So what we're about to do is a very general derivation and does not rely on this picture that I've drawn. What we're about to do is very general. This is just so you have something sort of intuitively in mind for the calculation that we're about to perform about the entropy and eventually the energy with respect to some internal constraint. So the variational statement is basically the following. If we have an isolated system, the internal constraint will assume its equilibrium value when the entropy is maximized. So isolated here would then mean that dE and dV here would be 0, but in general we're considering a non-equilibrium process here. So the fact that these are 0 isn't problematic. We can also have ds is not equal to 0 because we will be considering non-equilibrium states for this analysis. So the statement that entropy is maximal with respect to this internal constraint at equilibrium is basically the following statement. So we get del S, del lambda, as I've called it here, holding E and V constant. What this means, for it to be maximum, then the first derivative would then have to be 0. So we know we're at an extremum. And for it to be a maximum, we would then need the following equation, the second derivative with E and V held constant, to be negative. So this basically encompasses the variational statement of the second law of thermodynamics, and it's a very useful statement. So let's see what this statement then says about how energy behaves in a similar context. And in particular, we're wondering if energy has a special property, like if it's an extremum, for example, when we hold S and V fixed. And it turns out that this property here, the second law of thermodynamics, implies then that the energy would take a minimum value when the entropy and the volume are held fixed. So writing the first derivative of the energy with respect to the internal constraint when the entropy and the volume are held fixed then gives us the following equation. Now, because of the second law, this is 0, so the whole expression is 0. And so what that tells us is that the energy is at an extremum for the equilibrium configuration of lambda. But is it at a minimum or a maximum? Intuitively, you're probably guessing it's at a minimum, which it is, but let's quickly prove that. So looking specifically at the second derivative of energy with respect to our internal constraint here, we know, keeping the entropy and volume fixed, we get the following expression. So it's sort of a mouthful, but basically all we've done is we've just written out front the derivative with respect to lambda at constant entropy and volume applied to the expression that we had before for the first derivative of the energy. Now we could do a product rule, but what we do know is that at the equilibrium point, this will be at 0. So in fact, the only surviving term is the following, del E, del S, constant lambda and V, which we know this is just temperature. And this will be del lambda with inside our brackets, del S, del lambda. Evaluated at constant E and volume, and then this derivative is evaluated at constant S and volume. Oh, and I forgot a negative here. So this can be rewritten as temperature, and it would be tempting here to just call this the second derivative of entropy with respect to lambda, but notice that they're holding different values constant, right? So we can't immediately do that. And we'll have to dig into a little bit of our math for thermodynamics bag of tricks, and do a little bit of calculus here to arrive at our conclusion. So we're not ready to jump there yet. Okay, so let's just quickly tidy everything up. We have minus the temperature times what we have above. So del lambda okay. Now what we're going to do is we're going to call the inside of this bracket, we're going to call it B. Okay, so we have E is equal to minus T times del lambda B. And now we're going to reach into our bag of tricks here from the last video. And in particular, we're going to use the following identity. Now in this, what we're going to do is we're going to substitute x is equal to b, y is equal to lambda, so we get our equation from above, and of course t will be equal to the entropy, and Z will be equal to the energy. So plugging everything in, we get the following expression. Okay, so we have this this new expression. Now, at equilibrium, or the place that we're interested in, we know that this is at an extremum, so this is 0. So in particular, we get this identity, which is exactly what we wanted. It tells us that we can do exactly what we sort of probably wanted to do at the very beginning. In particular, what it says, what this allows us to do is we get the following expression, which tells us that energy is at a minimum. Okay, and we know that it is at a minimum because this is going to be negative, so the whole expression will be positive, giving us a minimum. So E is at a minimum at constant volume and entropy with respect to varying the internal constraints and arriving at your equilibrium point. This is actually a property that we'll find for the other free energies, and it's a property of so-called thermodynamic potentials. And so when we have internal constraints and those internal constraints are allowed to relax, energy is found to be at a minimum. And so with that, this is all I had planned for this video. Let me know what you thought. If you liked the video, feel free to like, subscribe, and leave a comment below. And I'll see you for the next lecture.